Okay, welcome everybody. Today I'm going to start with the very first lecture here that is going to be about momentum and kinetic energy. Recall, I am simply going to go through some of the background physics that I believe is necessary in order to actually understand many of the concepts that are uh, at the heart of quantum mechanics, at least in the introductory level of quantum mechanics. So we're going to start with momentum and kinetic energy, Ke for kinetic energy, and we do know two relationships here. Recall from classical mechanics, which I do expect the students to know for this course, the linear momentum of any particle with mass is classically equal to the mass of that particle times the velocity of the particle. So if you know the mass and you know the velocity of the particle, in classical mechanics you can really just, you can calculate what this momentum is. And of course the units of momenta are simply in kilograms times meters per second. And throughout this course you're going to see me put my units in brackets here. This is this is something that I am used to doing because it really helps me understand kind of what, doing some sort of dimensional analysis along the process of doing physics actually helps intuitively. And so I'm going to do that for you guys here today as well. And throughout the whole course because I really think it's useful. But anyways, this is just for you to know. Moving on. So we know that this is the momentum of any particle with mass. And we also know that the kinetic energy of a particle is equal to 1/2 mv squared. And notice I don't put a vector here because that vector quality is really lost whenever you square something. And so this is the kinetic energy, Ke for kinetic energy, of a particle. And of course, the unit of this is in joules, right? So we have joules, which is equal to, kilograms and meters squared per second squared. So it's another way of writing joules. And so we have two relationships here that we're going to kind of borrow throughout the course of quantum mechanics, and it's rather critical for everyone to understand what this is here and what it represents clearly. We have a particle with the momentum p, and that momentum that particle actually has a kinetic energy that is proportional to it. And to be a bit more precise, we can rewrite this kinetic energy in terms of momentum. And so clearly they're related through this velocity here. And we can write that as Ke, e to the Ke, is equal to p, the vector p, dotted with the vector p, right, over 2m, and that's simply equal to p squared over 2m. Right, and we can really check this. It's not that big of a deal. You can simply substitute mv for p here, and then you'll realize that you just get 1/2 mv squared in the end. And so we have our kinetic energy, which we can write in terms of momentum, and we can write in terms of velocity. And so this here is once again our kinetic energy, and it's a critical component. It actually comes up, as you will see, in the actual Schrodinger's equation, which we'll be looking at it later in the course. We're going to be looking at this relationship here will come back. So moving forward just a bit. So we're just again, we're just reviewing here, really. Now, moving forward, we're going to be discussing here force and potential energy. So, of course, we have our potential energy. That's the other sort of component of a total energy of a particle. You have the kinetic energy, and then you have the potential energy, of course. And you also have this force relationship. And so We do know from Newtonian mechanics that the force of any applied force of a particle is equal to its mass times its acceleration. Now notice I put like a bar up here whenever there's a vector, as usual. And this acceleration term, of course, can be written as mass times d squared x, this is along one dimension, let's say, over dt squared. So it's the second derivative of position with respect to time. This gives us our acceleration. And of course, this can also actually be written as m times d squared, or not d squared, I'm sorry, dv dt. So the first derivative of velocity also gives you acceleration, right? But we do recall from the relationship above that the momentum was equal to m times v, right? And so we can actually, it turns out we can rewrite this term here, dmv over dt. We can rewrite this as dp, or sorry about that. We can rewrite this as dp dt. So F, the force applied on a particle, is simply equal to the momentum, the change in momentum over the change in time, with respect to time. So the change in momentum with respect to time is simply another way of writing, Newton's second law, right? And so we have F equals ma. That's also written as F is equal to dp dt. Yes? And now I'm going to introduce to you guys another pretty simple concept. And here we're going to take this force and relate it to a potential energy. So how can we relate force and potential energy? So recall, we can actually take the case of a particular ramp. So let's say we have a ramp, right? Here I'm going to draw some expression that relates force and potential energy, and we're going to see why we want to do this. Right, so let's pretend we have a ramp. This is a classical case, and let's say we have a ball on top of this ramp. Or actually, let's say we have a ball right here on the top of this ramp. They're in the middle, right? We have a ball there. And let's pretend that we're applying a force called F of px. So I call it px for like push, a pushed force. So let's say I'm applying a force here in this direction. And if I apply a force in this direction, we can presume that, well, at any instance of time, t, the ball is going to displace itself a distance of delta x, right? So if I apply a constant force with any given time t, obviously I'm going to have a displacement delta x, and so the ball will ultimately appear here. And so what does that mean? Well, the force that I apply on any given particle, if I apply a force on any particle, it will displace itself delta x, and it actually turns out, since the force is equal to newtons, right, and if the distance, of course, is in units of meters, Newton meters actually is a unit of energy. And this unit of energy comes in the form, so if I'm adding energy to this particle with mass, that comes in the form of potential energy. That added energy is in the form of potential energy. And we're going to call that potential energy, we're going to label it V, our variable V, which is a common variable for potential energy. So we're going to call that delta V, right? Delta V, right? So delta V, this gives us joules, of course, right? This is potential energy, it's in joules. And we can rewrite this as F of Px is equal to delta V over delta x. And in the limit of a very, very tiny displacement and thus a very, very tiny change in potential energy, I will get dV dx, this differential expression. So I know now that the force is equal to dV dx. Now note that this is simply a force in the opposite direction. Gravity also applies a force in the negative direction, an equal and opposite force in the negative direction, right? And so if I, simply care about the force in the bottom direction, right? Not the positive component. So we're labeling this as positive, right? The force of x, I'm going to call it F of x here, F sub x. This force is simply the force due to gravity, in the case of this ramp, and that's going to be equal to then simply the negative of dV dx. Right. This, regardless of, depending on how you want to write this, it really just depends on your convention. It's most commonly, obviously, I'm not sitting here constantly applying a force. Oftentimes when we're analyzing these problems, it is a ball that is placed here and it's let go. And so the displacement of the ball is in the so-called negative direction. And so this is the most often expression that you tend to see in textbooks. F of x is equal to minus dV dt. And if we generalize this on all three dimensions, we have this expression f, and of course these are all vectors. These are all vectors. F is equal to nabla v. This is simply, this term, this upside down triangle is simply the derivative in all three dimensions. So if you guys recall, this del operator here is equal to d squared dx squared plus d squared dy squared plus d squared dz squared, of course, right? So this is simply, that's the relationship here. And this is ultimately the force. And so once again, we're going through a review here, folks. We're simply defining some of the very common relationships in between force and kinetic and potential energy. And in the previous review here, we went through the relationship between kinetic energy and momentum, right? And so this is, we're going to have several problems of this, and we're going to realize why this particular analogy, or this particular problem here of this ramp in a ball is actually important in quantum mechanics. And the reason is because we can actually have a direct analogy between this ball in a ramp and an electron and an electric field. Right, and so the analogy here would actually be, I'm going to draw this analogy really quickly here, but we're going to get back to this, is if I have an electron here and I have a positive electric field. So let me see, I'm just trying to determine how to draw this for you guys. So I can have a positive electric field, I could have a plate here, I could apply a positive bias, and I can have a plate here, or a negative bias. And I can have, of course, this electric field. I can have all these electric field lines, right, from the positive and the negative direction. This electron here sees this, the potential landscape of this system here is very similar to the potential landscape of this system over here. In other words, if I want to determine what the kinetic energy is of a ball that is dropped from the top and arrives to the bottom. So I have a ball here, and I want to say, okay, once the ball arrives all the way to the top, what is the kinetic energy of the ball the moment it hits the bottom of the ramp? Well, it turns out that the mathematics, which is over here on the right, is identical to the math that I would need to determine what the kinetic energy of the electron would be the moment the electron arrives to the other side of the plate, right? And oh, of course, I just realized that you know, mix these up, but you get the point, right? You get negative, 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 positive, 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 and of course the electric field lines are, I got the electric field lines right, but you get the point, right? They're in this direction. This is how it looks like, right? And so the electron, of course, would be repelled away from all of this negative charge toward the positive charge. And so it's this particular system, these two systems are very much identical. And so this is a very nice way to actually understand the concept of an electron volt, right? And we're going to get back to this, but it's a really great way to understand the concept of an electron volt. And we're going to have a problem that actually tackles this concept directly. And so that's the end of this lecture, and I'll see you guys in the next one.